Paris. She will speak on the mathematical study of the non-relativistic limit of a relativistic mean field model for nucleons.
Thank you. First of all, I would like to thank the organizer for inviting me here in Cambridge. Today, I will present a mathematical study of a particular non-relativistic limit of a relativistic mean field model for the atomic nucleus. This talk is based on two joint works with Maria Esteban. The first one is on archive under this reference, and the second one is still in preparation. Here the outline of my talk. First, I will introduce the relativistic mean field theory, and I will give a formal derivation of the nuclear physics non-relativistic limit. Then, I will present our result in the spherical symmetric case and in the general three-dimensional case. Next, I will discuss some numerical aspects and qualitative properties of the symmetric ground state. And finally, I will conclude with some open questions. In nuclear physics, the relativistic mean field model describes the atomic nucleus as a system of Dirac particles which interact in a relativistic way via the exchange of virtual particles called mesons and photons. The relativistic model can be considered as a generalization of some non-relativistic models, such as the Kirme or the Gogny-Force-Hartree-Fock model, where the instantaneous forces are replaced by a mean potential. The relativistic model describes successfully the structure of nuclei as the non-relativistic ones, and provides a natural explanation of some relativistic effects, such as the spin-orbit force. The relativistic mean field theory is formulated on the basis of two approximations, the mean field approximation and the no-C approximation. On the one hand, thanks to the mean field approximation, the nucleons behave as non-interactive particles which move in a mean field created by mesons and photons. On the other hand, thanks to the no-C approximation, the vacuum polarization is neglected. These approximations are reasonable because the relativistic mean field theory is an effective theory. That means that the parameter of the model must be adjusted on experimental data. In this way, the vacuum polarization and the correlation effects are taken into account implicitly. In the model that I will present today, I consider the sigma meson, which provides a medium range attractive interaction, and the omega meson, which describes a short range repulsive interaction. The equation of this model, called sigma meson model, are the following one. Here, m is the nucleon's mass, c is the speed of light, Cj are the wave function for the nucleons, and rho s and rho 0 are a density which are defined in this way, where A is the number of nucleons. M sigma, M omega are the masses of the mesons, and J sigma, J omega are the coupling constant. M sigma, M omega, J sigma, and J omega are the parameters of the model. The differential operator here in the first equation is the Dirac operator. I remind that the Dirac operator is a first-order differential operator whose spectrum is not bounded from below. And the Dirac representation, beta, is a 4x4 matrix defined in this way, and alpha bold is a vector of three 4x4 matrices defined via the Pauli matrices sigma k. Then, for the nucleus, we have a non-linear Dirac equation, while for the mesons, we have Klein-Gordon equations. The goal here is to study a particular non-relativistic limit of this model. And this particular non-relativistic limit is obtained formally in this way. Let me consider the case of only one nucleon. To obtain the nuclear physics non-relativistic limit, I have to pass to the limit as c goes to infinity in a particular regime for the parameters of the model. Then first, we suppose that the energy mu of the nucleons is much less than mc squared. Then we write the Dirac spinor as spinor up phi and spinor down chi, and as a consequence the scalar density rho s and the scalar density rho 0 can be written in this way. With this decomposition here, we can decompose the Dirac equation in the following system, where sigma bold is the vector of Pauli matrices. Now, I would like to write chi from the second equation and replace it in the first one. To do this, I have to suppose that the 2mc squared plus s minus v minus mu is never equal to 0. And if I suppose this fact, I can write chi in this way here. To obtain the non-relativistic limit of the Dirac equation, I have to expand this denominator here with respect to a parameter that is small when c goes to infinity. In atomic physics, we consider that s minus v minus mu over 2mc squared is small when c goes to infinity. But this approximation is not acceptable in nuclear physics because s minus v is large. Indeed, if c goes to infinity, s and v can be developed in this way. And in particular, s is proportional to the scalar density rho s, and v is proportional to the vector density rho 0. According to the physical value, to the value that we find in physics literature, we can suppose that the coupling constant J sigma J omega and the meson masses S m sigma m omega behave in this way here. See, for example, the papers of Reiner and Ring. And if we do this, we have the following expressions here for S plus V and for S minus V. Then we see that as C goes to infinity, S minus V is proportional to C squared. By using this expression, we can write the following system here. Now, we suppose that the quantity lambda rho 0 over C squared goes to 0 as C goes to infinity. And by dividing the second equation here by C, we obtain this system. Before passing to the limit as C goes to infinity, we have to remove the dependence on C here in front of key, and here, and also in this term here. To do this, we use the following rescaling for the wave function, and passing to the limit as C goes to infinity, we obtain this system that is the object of our study. We remark that here the parameter A depends on the mass of nucleon and on the mass of on the masses of mesons and on the coupling constant, while B depends only on the mass and the energy of the nucleon. Starting from this system, we can write tilde key as a function of phi tilde, and we obtain this limit equation that is the nuclear physics non-relativistic limit of the relativistic mean field model. Why this equation is so interesting? First, the non-relativistic limit equation can be studied in an easier way than the relativistic one, but it still contains some relativistic effects, as for example the spin orbit term. Indeed, if we analyze more in detail this operator here, we can write the following expression. Okay, we can develop the operator and write directly this. And I can do this by using only the properties of polymetrics. And here I obtain this term, that is the spin orbit term. P for me is minus C gradient. Moreover, some qualitative properties of the mesonic potential can be deduced from the solution of this model. And from a mathematical point of view, we have to deal with the nonlinear Schrödinger type equation where the mass depends on the point x in the R-free space. Now, then, we have a new model, we have a new interesting model, and the first thing that we want to do is to prove the existence of solution for this model. Let me start by looking for solutions which are separable in spherical coordinates. And more precisely, I look for solution of this form where G and F are real radial functions. In this case, the nuclear physics non-relativistic limit is a first-order dynamical system. Is this first-order dynamical system. Moreover, to avoid solution with singularity at origin, I suppose that F0 is equal to 0, and since psi must be square integrable, I look for solutions such that F and G go to 0 as R goes to infinity. The result that we obtain in this spherically symmetric case is the following theorem, which asserts that if A is bigger than 2B, then there exists a solution of the system such that F0 is equal to 0 and such that F and G satisfy this inequality. That implies that F and G go to 0 as R goes to infinity. This theorem and its proof are similar to a result of Cazenave-Vasquez that they obtained for the solar model, which involves a nonlinear Dirac equation. The main difference is that in our case, we have a boundless constraint for the initial values of G. Because of these constraints, we have to deal with additional difficulties, and the new strategy of proof is needed. Here, in the theorem, we have a condition on the parameter A and B, and one can naturally ask why we need this kind of condition. The answer to this question is given by this proposition, which asserts that A bigger than 2B is a necessary condition for the existence of non-trivial solution with finite energy. And moreover, this proposition gives also a bound for the initial value of the function G. The key ingredients of the proof of this proposition are the analysis of the relative conservative system associated to the object of our study and the behavior of the Hamiltonian energy. More precisely, there is a conservative system associated to the system that we want to study, that is the following one. And this system is an Hamiltonian system where the Hamiltonian energy is defined by this expression, where I call F the part of the energy that depends only on G. By a straightforward calculation, we obtain this lemma, which gives the behavior of the Hamiltonian function, the Hamiltonian energy, when Fx and Gx are solution of the system with initial condition 0x. Then, to study this conservative system, it's enough to draw the phase portrait. Here, the phase portraits of the system for the different values of A and B. The gray part here represents the region with negative energy. The goal is to show that in all these cases here, we cannot have solution with finite energy. Then let me consider, for for example, the case where A is bigger than B and smaller than 2B. And suppose by contradiction that there exists a solution with finite energy. That means that we have fx gx such that the limit as r goes to infinity of fx r gx r is equal to 0. That means that there exists a delta bar such that for all r bigger than delta bar, the absolute value of gx r is smaller than 1. And because in this region here, between 1 and minus 1, the energy non-increasing, we have also that the energy of fxr gxr is bigger than the energy, the limit of the energy as r goes to infinity. Then it's bigger or equal than 0. Now suppose that the initial condition is in the gray part here. That means that the initial condition is such that the energy is negative. Then, because of this fact, there exists an Rx such that the energy is 0 and the absolute value of Gx is smaller than 1. But in the neighborhood of this point, we have a contradiction because we pass from a point with negative Hamiltonian energy to a point with energy equal to 0 in a region where the energy is non-increasing. Then we have a contradiction in this case. Now suppose that the initial condition is here in the white part. That means that H0x is positive and x, the absolute value of x is bigger than 1. But in this case, because of this condition, there exists a finite time Rx such that the Gx Rx is equal to 1. And then the energy in this point, as we can see here, in 1, the energy is negative. And then we have again a contradiction. In this way, then, we can exclude all these cases here. And to conclude, it remains to exclude the case where A is equal to 2B. For this, we need this lemma, which asserts that if the absolute value of x is bigger than 1, then the absolute value of Jx is bigger than 1 for all r bigger than 0. This lemma is proved by using the monotonicity of the Hamiltonian energy and of the function that I call f. And with this lemma, we can exclude also this case because the initial condition cannot be here, since in this case Jx r is bigger than 1. That cannot be equal to 1 because the unique solution with initial condition equal to 1 is Jx r equal to 1 for all r. And that cannot be here because of the same reason. Then the only possibility is to have A bigger than 2B. And in this case, using again the monotonicity of the Hamiltonian energy and of the function f, we obtain this lemma, which asserts that if the absolute value of x is smaller than 1, then the absolute value of x of jxr is smaller than 1 too. And this gives a boundedness constraint on the initial value for the function g. Then it remains to show that this condition, a minus 2b bigger than 0, is a sufficient condition for the existence of a solution fj with finite energy, and such that f0 is equal to 0. Our proof shows also that f is always negative and g is always positive and smaller than 1. To prove this fact, we use a shooting method. Let me give a sketch of this proof. The first step is to show that there exists a solution of the system fx_jx such that fx_rx is equal to 0 for some finite time rx, and fx is negative and jx is positive for all time before rx. This means that the solution behaves in this way. Let I the set of initial conditions for which the solution behaves in this way. Then we show that if x goes to 1, the solution stays for a long time close to g equal to 1, and then there exists a finite time Sx such that jxxx is equal to 0. This implies that the supremum of the set I is strictly smaller than 1. Actually, this is the main difficulty to deal with, and in this part of the proof, contains the novelties of our argument. In fact, once we prove that the supremum of I is smaller than 1, we can conclude by taking this quantity as initial condition for the solution. In this way, we proved the existence of spherically symmetric solution of the nuclear physics non-relativistic limit. Then, what about the solution in the general three-dimensional case? We remark that the limit equation is the Euler-Lagrange equation of this energy functional under this normalization constraint. Unfortunately, this energy functional under this constraint is not bounded from below. In the set of functions for which the energy f is finite. Then we are faced with two problems. One, how to solve the limit equation, and second, how to give a good definition of the ground state. In the spherically symmetric case, we remarked that if A is bigger than 2b and phi is a solution of the limit equation, then the norm of phi is strictly smaller than 1. In this way, I can add a positive part here in the kinetic term of the energy functional without changing it. And in this way, I define a new energy functional E. This energy functional is bounded from below under the normalization constraint in this set of functions. Then the ground state can be defined as the solution of the limit equation which minimize the energy f among the functions that are solution of the limit equation. Inspired by this fact, we want to find a solution of this minimization problem, this new minimization problem. Let me stress the fact that here I add a positive part in the denominator of this function, of this energy function. And x is the set of functions for which this energy function is finite. A solution of this minimization problem is a solution of this equation with the positive part in the denominator here. But thanks to this lemma, if phi is in this set here, then the norm of phi is smaller than 1 almost everywhere in R3. And then phi is a solution of this equation, that is the nuclear physics non-relativistic limit. Then to find a solution of the nuclear physics non-relativistic limit without ansatz on the form of the solution, we have to minimize, we have to find a solution of this problem here. And for this, we have this theorem, which asserts that if I is smaller than 0, then there exists a minimizer of this problem. Moreover, I is smaller than 0 if and only if A is big enough. And in particular, A must be bigger than 2 over S squared, where S is the best constant in Sobolev embedding of H1 in LCs. The idea of the proof is to use a concentration compactness argument with some new ingredients to deal with the possible singularities in this kinetic term here. And in particular, we have to choose other cutoff functions to rule out the dichotomic case. Then now we have found a solution, we have proved the existence of a solution in the general case. It's remained to give a good definition of the ground state. Unfortunately, we are not able to completely answer to this question. We know how to define a ground state in the spherically symmetric case and in this intermediate model. Suppose that phi has this form here, where U is a real function, not necessarily radial. And suppose that phi is a solution of the non-relativistic limit. Then phi is a solution of this equation here. Now define Tk as the truncation function for all k bigger than 1 and multiply this equation by phi times Tk phi squared in L2. By doing this, we find this expression here, and since the gradient of Tk phi squared is given by this expression, if A is bigger than B, then the left-hand side of this expression is negative. And then each term here have to be equal to 0. That means that either phi squared is smaller than 1 or phi squared is bigger than k almost everywhere. But by taking to the limit as k goes to infinity, we obtain that phi squared is smaller than 1 always everywhere, and that means that f phi is equal to E phi. Then in this model, the ground state is the solution of the equation which minimizes the energy f among the functions that are solution of the limit equation, again as in the spherically symmetric case. To conclude, let me discuss some numerical aspects for the spherically symmetric case. In computation carried out in physics, it has been observed that the fields of meson sigma and omega are proportional to the scalar and vector density as in our model. Moreover, the potential V and the potential S behaves as a plateau-like Saxon-Woods potential. That means in this way. More or less in this way. And the intensity of the potential V minus S is much higher than the intensity of the potential V plus S. In the numerical calculation that we ran out for our model, we observed that if A and B are well chosen, then the Saxon-Wood shape for the potential V and S is perfectly observable, and the intensity of V minus S is much larger than the intensity of V plus S. Take, for example, A equal to 9 and B equal to 4. Then G square and F square behaves in this way here. But as C goes to infinity, we know that S is proportional to, is more or less as minus mc squared G squared, and V is more or less as plus mc squared G squared. Then V and S behave like a plateau if G squared does, as in this case here. And from this expression, we see that the intensity of V minus S is of order C squared, while the intensity of V plus S is of order 1. Then in this case, when A is equal to 9, B is equal to 4, the qualitative properties of the mesonic potential are perfectly observable. A less clear case is the following one, where A is equal to 4 and B is equal to 1. Here, neither G squared, neither F squared has a plateau-like shape. Other computations that we ran out show that the plateau shape is more and more present when 2b of A is close to 1. And it's normal because I say that when the initial condition is close to 1, then the solutions stay close to G equal to 1 for a long time. And then we have a plateau shape. And my last slide is for some open problem. First of all, we would like to give a good definition of ground state in all the cases, and for this we would like to show that if phi is a solution of the limit equation, then the square of the norm of phi is smaller or equal than 1 almost everywhere. Next, we have to treat the case of A bigger than 1. And finally, we have to give a rigorous derivation of the limit equation, but for this, we need some a priori estimates on the solution of the relativistic field equations. And thank you very much for your attention.
Yeah, thank you very much. Are there any questions or comments?
What's the reason for picking the omega and sigma meson and not taking pions, which are lightest? And I'm going right back to the model, I guess.
Yeah, yes. Okay. Well, the sigma omega model is the easier model, is the easier relativistic mean field model, and the two mesons are necessary because the sigma meson describe an attractive interaction, and the omega meson describe a repulsive interaction. Then we need the two for have a good model, and this one is the simplest that we can take in the relativistic mean field theory.
And so if you found a bound state, would you interpret it as a proton or a neutron? Or?
Here it's only one nucleon, then it can be a proton or a neutron.
You don't care either?
Yeah, no. And also because we don't consider the rho meson, that is the meson that make a difference between proton and neutron. And we don't consider the electromagnetic field that again make a difference between proton and neutron. Then here is it doesn't care if the nucleon is a proton or a neutron.
I have a question actually. So when you split the Dirac equation by looking at the top and the bottom spin, you were dividing by some expression, right, which you
Yes.
assumed not to be zero. So is that likely to be a problem eventually then with the fields S and E?
Yes, to do this formally we need some a priori estimates on the solution that we don't have for the moment. But
no, but I mean, in the end you get some solutions S and B, and for these solutions you don't have zero step. Did you check this?
you mean here? When I have the limit equation, you mean here? I don't have in the spherically symmetric case, no, because I show that in the spherically symmetric case, this quantity is strictly smaller than 1. I don't have problem in the spherically symmetric case. Your question is linked to the fact, to the definition of the ground state. The idea it's really to show that also in this equation, phi square is smaller or equal than 1 almost everywhere. But, we don't know how to do it.
Any other questions? Well, if not, then let's thank the speaker again.